Here we start with miscellaneous exercise 5. First question. The question number 1 is you simplify this expression, evaluate this. So what we do is here, you know iota square is minus 1 and iota raised to 4 is 1. So we use this concept and we reduce either in form of 2 or 4. So that raised to 18 you can write as here raised to 16 into iota square plus this is 1 upon iota raised to 24 into 1 upon iota. The whole cube right now will keep as it is. Now this iota raised to 16 is just 1 and this is minus 1. Why iota raised to 16 is 1? Because you can write iota raised to 4 raised to 4. So this is 1 raised to 4 and that is just 1. What about this? Iota raised to 24, that is iota raised to 4, the whole raised to 6. That is 1 raised to 6. So that is again 1. So here this is minus 1. This is just 1 into 1 upon iota, the whole cube. Now at this place, here this is minus 1. We rationalize this. Rationalizing means multiplying dividing with iota. Why we are doing this? Because you know that now this is iota squared, which is minus 1. This much is minus 1. So this is minus iota whole cube because this is iota square, so minus 1. I'll take minus common here, so it will come as minus here 1 plus iota the whole cube. Now we expand this using a plus b the whole cube. So you know 1 cube plus iota cube plus 3 times 1 square into iota plus 3 times 1 into iota square. Now here minus 1 as it is. This is 1. This is iota square into iota, but iota square is minus 1. So this is just minus iota plus 3 iota. This is minus 1. So this is minus 3. So finally you are getting minus 1 into over here. This is nothing but the minus 2 plus 2 iota. So if I take this minus inside, this is 2 minus 2 iota. This is the final simplification here. In the next question, you want to prove this for any two complex numbers, real part of z1 into z2 equals to this expression. So we'll take any two complex numbers. Let's take z1 equals to in general a plus iota b. This is in general any complex number. And z2 equals to, I'll take c plus iota d, where a, b, c, d all are real numbers. Any complex number randomly, remember. Okay, now we find their product first, that is z1 into z2. You know that this is called real part, this is called imaginary part. Real part, imaginary part. You need real part of z1, z2. So we'll find here a plus ib into c plus id. I'm just multiplying here. This into this ac, this into this which is minus bd, because you will get iota square, plus ad plus bc, and I'll find iota common. So this is z1 into z2. Now you want the real part of this one. So our LHS would be real part of z1 into z2. That is this first number, which is AC minus BD. Call this as 1. Okay. Now, what about RHS? Look at it, RHS. So RHS is here the real part of Z1 into real part of Z2 minus imaginary part of Z1 into imaginary part of Z2. What is real part of Z1? That is A. Imaginary part of Z2, which is D. Sorry, real part of Z2, which is C, minus imaginary part of Z1, which is B. Imaginary part of Z2, which is D. This is 2. So from 1 and 2 here, you have LHS equals to RHS. So shown that the both are equal. We go to question number 3 now. Third question here. Let me call that as complex number z here. Z equals to, you have 1 upon 1 minus 4 iota minus 2 upon 1 plus iota into 3 minus 4 iota upon 5 plus iota. This is a complex number because iota is involved. So we just simplify and we'll show that it is in a plus ib form. That is the question. We want to reduce and short in a plus ib form. So it's a simple algebra. You need to do it carefully, remember. Okay, so I'll simplify first this round bracket, cross multiplication here, 1 plus iota, here minus 2 plus 8 iota, cross multiplication, 1 minus 4 iota into 1 plus iota, into this one as it is here. Right now, this expression as it is. So what we'll get here, if you just simplify, 1 minus 2, this is minus 1, plus 9 iota into, I'll open this bracket here, 1 into 1, 1, this multiplied with this, so here 4 iota squared, but iota square is minus 1, so 1 plus 4. Then this with this, which is iota minus 4 iota. So this gives you minus 3 iota into, right now, this expression as it is. Okay. Now this is equals to minus 1 plus 9 iota upon 5, here 5 minus 3 iota into 3 minus 4 iota upon 5 plus iota. So now if I continue with further simplification, now what we do is here, we just open the brackets in the numerator and denominator. Right? So how do I open? As we were doing in numbers, minus 1 here, minus 3, so this is minus 3, this into this, which is minus 36 iota, so plus 36, plus minus 1 multiplied with this, which is 4 iota, and this is plus 27 iota upon here 5, that is 25, 3i and I, so it is minus 3 iota square, but iota square is minus 1, so here plus 3, here plus this into this, which is 5 iota, and this is nothing but here minus 15 iota, so this is nothing but 33 plus this is 31 iota upon this is 28 minus 10 iota. Now what we do, as you know, in complex number, you multiply and divide by conjugate of the denominator. But before I do that, what I'll do, you can see that there is 2 common, so I'll take 1 by 2 outside here, 33 plus 31 iota upon 14 minus 5 iota, 14 minus 5 iota. Now here multiplying and dividing with the conjugate of this is called rationalization, 5 iota upon 14 plus 5 iota. Now this is a repetition of previous step, this multiplied with this, and this expression is multiplied with this, 1 by 2 as it is, so I'm multiplying here. So here 33 into 14, this into this, which is 462, 31 into 5, which is 155 iota square, so minus 155, plus now terms involving iota, 33 into 5, and this 31 into 14. So if you do this, you will get the 434 plus 165 into iota. This with this and this with this term involving iota. Just open the brackets, you will realize, and use iota squared equals to -1 upon same thing here. But this, this is z into a z bar, which is a square plus b square. So 14 square plus 5 square. This concept here. Z into z bar is x square plus y square. I've used this concept here. Okay. So this is 1 by 2. Here, this is nothing but the 307 plus here. This is nothing but 5. This is 599 iota upon. This is nothing but 221 if you add these two. So finally you get the 301 plus 599 iota divided by this into this, which is 442. This is the simplified form. If you want, you can add one more step. 307 upon 442 plus 599 upon 442 iota. This is simplified form of the complex number, a plus ib form. Okay. Next question, question number 4, fourth question. That's an important example. You are given this x minus iota equals to square root of a minus iota b and c minus iota d. First, I'll just square on both the sides. So x minus iota the whole square equals to a minus iota b upon c minus iota d. Squaring on both the sides, just to make the RHS free from the square root, remember. Okay, now if you just observe the required expression, you want x square plus y square on the RHS. Now that is nothing but the modulus of this. You want a square plus b square if you just notice RHS. So that is the magnitude of this. So what I'll do, taking modulus on both the sides. Taking modulus on both the sides. Okay, so I'm taking modulus on both the sides. So what happens if I take modulus here? Modulus of x minus iota y the whole square equals to modulus of a minus iota b upon c minus iota d. What's the modulus of a complex number? That is root of x square plus y square, the whole square as it is. Here, modulus of the numerator, which is root of a square plus b square, upon modulus of the denominator, which is root of c square plus d square. Here you have used this concept, remember. Modulus of z1 upon z2 equals to modulus of the numerator upon modulus of the denominator. That formula you have used indirectly. So now I think you are through. This will get cancelled. X square plus y square equals to, you are getting root of this expression. Now if you just observe the required expression, squaring on both the sides. Squaring on both the sides. So we are getting this. Okay, question number 5 is about to get the polar form of a given complex number. To get the polar form means what? You find r and theta. You need to find what is r and what is argument. These two things you need to get. So to get r and theta, this should be expressed in a plus ib form. So I'm doing that as we did in the previous question, simplification, multiplying and dividing with the conjugate here. 1 plus 2 iota upon 1 plus 2 iota. What is this? This is z into its conjugate, which is a x square plus y square. So 1 plus 4. Here I'll open these two brackets. So 1 into 1, 1 3 iota into 2 iota, which is nothing but the 6 iota square. So into minus 6. Now term involving iota here. So this is 2 iota plus 3 iota, which is 5 iota here. 1 into 1. This is 6 iota square, which is minus 6. And here 3 iota plus 2 iota, so 5 iota. So z equals to, this is 5 plus 5 iota upon 5. And z equals to, finally if you do individual division, you are getting 1, oh sorry, this is minus 5. So minus 1 plus iota. This is a plus ib form. Now we find r and theta as we were doing. So what is here r? R is modulus of z, which is real part plus imaginary part. So minus 1 square plus 1 square, which is root 2. Okay, so r is root 2. Now to get the theta, we use this concept, cos theta equals to, you know, x by r. And what is sin theta? That is y by r, that you know. So therefore cos theta equals to, what is x? X is nothing but minus 1 by root 2. What is y? That is nothing but the 1 by root 2. So here, forget about signs right now. Both are 1 by root 2, 1 by root 2. So it has to be pi by 4. Cos negative, sin positive. So theta is in which quadrant? Is in second quadrant. Cos negative, sin positive. So theta is in second quadrant. Second quadrant means pi minus something. So theta will be, here you know pi, minus something. What is that something? That is 1 by root 2, 1 by root 2 means pi by 4. So your theta is 3 pi by 4. So therefore polar form is here. You know polar form is z equals to r inside the bracket cos theta plus I sin theta. But what is r? That is nothing but the root 2. So root 2 into cosine 3 pi by 4 plus I sin 3 pi by 4. This is the final required polar form, the given complex number. How you will do the first question? I'll just show you one step. For first question, let's take z equals to 1 plus 7 iota upon 2 minus iota whole square. So first you expand this. So 1 plus 7 iota upon x minus y the whole square. So 4. What is the middle term here? Minus 4 iota. Last term is iota square. So 1 plus 7 iota upon, this is minus 1. So this is 3 minus 4 iota. And now you simplify like the previous question, multiplying and dividing by conjugate of 3 minus iota. So we have this. Now denominator, that is z into its conjugate. So x square plus y square. So 9 plus 16, 25. Open these two brackets, so we'll get a plus ib form, and then just continue. Question number 6, 7 and 8 are about quadratic equations. Even I suppose 9 also. 6 to 9. These questions are about quadratic equations. So I'll do just one of them. Let me do the question number, for example 7. So that's x squared minus 2x plus 3 by 2 equals to 0. I'll take 2 as LCM here. So 2x squared minus 4x plus 3 equals to 0. So here a is 2, b is minus 4 and c is 3. Right. Quadratic equation, you know, ax squared plus bx plus c. Now we will find the discriminant, which is b square minus 4ac. b square means 16 minus 4a into c. So here 16 minus this is 8, 24. So this is minus 8. So this is negative here. So roots must be complex. Okay. So therefore here you can call the solutions or roots which is given by minus b plus or minus b square minus 4ac upon 2a minus b. So this is plus 4 plus or minus, this is minus 8 upon 2 into 2. So you are getting 4 plus or minus, you know this is root 8 iota, because you know root minus 1 is iota. We did this, so you know it. Upon 4. So 4 plus, you know root 8, you can write 2 root 2 by 4. If you want to do individual division, 1 plus or minus root 2 by 2 iota, 1, 2 will get cancelled. These are the roots, these are the complex numbers, which are the roots of the given quadratic equations or solutions. Okay. Question number 10, which is a very simple question here. So 10th question, you are given z1 equals to 2 minus iota and z2 equals to 1 plus iota, and you want the magnitude of z1 plus z2 plus 1 upon z1 minus z2 plus 1. So we'll find this and we'll just express in a plus ib form. So 2 minus iota plus 1 plus iota plus 1 upon 2 minus iota minus 1 minus iota plus 1. So here numerator expression will be iota iota will get cancelled, 2 plus 1 plus 1, that is 4 upon, here this will goes away, 2 minus 2 iota, 1 2 will get cancelled here, so 2 upon here 1 minus iota. Now this means modulus of 2, which is 2 upon modulus of 1 minus iota. So this is 2 upon, this is root of 1 plus 1, real part square plus imaginary part. So 2 upon root 2. So here this is just root 2. This is the simplification here of the given expression. Question number 11 is, if you just observe, a plus iota b equals to x plus iota the whole square upon 2x square plus 1. This is real number, there is no iota, remember. If you see the required expression, you want a square plus b square, that is the magnitude of this. And x square plus 1 is the magnitude of this. So just take modulus on both the sides, taking magnitude on both the sides. Just refer question number 4, you will realize it's a copy of question number 4, you will see. So in the next question, you want real part of this complex number. That means this complex number should be expressed in which form? X plus iota y form. Then this x become real part. So we start with this here, and we express in x plus iota y form z1 z2 upon z1 conjugate. The main task is to express in x plus iota y form. What is z1? 2 minus iota minus 2 plus iota upon conjugate of z1. Conjugate means I is replaced by minus I, so 2 plus iota, remember. Now as we did earlier, we just simplify. So if I open the bracket here, this is minus 4 and this is minus iota square, so it becomes plus 1, plus this is 2 iota and this is also 2 iota, so 2 plus 2, 4 iota upon, right now 2 plus iota as it is, so this is nothing but the minus 3 plus 4 iota upon 2 plus iota. Now multiply and dividing by conjugate of this, that is 2 minus iota upon 2 minus iota. So what is denominator? Z into z bar, that is x square plus y square, which is 4 plus 1. Here you open these two brackets, so this is minus 6 minus 4 iota squared, which is plus 4. Now items, this is plus 3 iota and plus 8 iota. So 8 plus 3, which is 11 iota. So you are getting minus 2, this is just 5 here. Minus 2 by 5 plus 11 by 5 iota. That's a simplified form of the given complex number. And now real part of this, therefore real part of z1 into z2 upon z1 bar, which is minus 2 by 5, term which is free from iota. What about the second sub question? There you want imaginary part of 1 upon z1 into z1 conjugate. So you start with this, you express in x plus iota y form, and imaginary part means the coefficient of y, right? So important task is just to express in x plus iota y form and then write the coefficient of y, so we'll get the imaginary part. Question number 13, you are given this complex number, you are asked to find the modulus and argument. So what we do, as you know, we need to express in x plus iota y form. So 1 plus 2 iota upon 1 minus 3 iota into multiplying and dividing with its conjugate. You know this is very commonly used method now. This is z into its conjugate, which is x square plus y square, you know. So here what we'll get? 1 plus 9. That's the advantage of doing this. This into this is 1 here. This is 6 iota square, so minus 6 plus, now this is 3 iota, this is 2 iota, so we'll get the 5 iota here. So you have minus 5 plus 5 iota upon 10. So do individual division. So minus 1 by 2 plus 1 by 2 iota, this is z here. Now we get modulus here, which is modulus of z, which is root of 1 by 4 plus 1 by 4. So this is nothing but, you know, root of 2 by 4, which is 1 by 2. So that is 1 by root 2. That is modulus of z. And for theta, we use this relation cos theta equals to x by r minus 1 by 2 upon 1 by root 2. And sin theta equals to y by r 1 by 2 upon 1 by root 2. So therefore cos theta will be here, 1 root 2 will get cancelled, so we are left with minus 1 by root 2, and here sin theta equals to again 1 by root 2. Cos negative, sin positive, so theta will be in which quadrant? You know, second quadrant. Therefore, as we did here, second quadrant means pi minus something, so pi minus, here your pi. For what value of the theta, cos theta and sin theta both will be 1 by root 2, that is pi by 4. So your argument is 3 pi by 4. In the next question number 14, you are given that x minus iy into 3 plus 5 iota is the conjugate of this complex number. This is conjugate of this. That means x minus iota into 3 plus 5 iota is conjugate of this. So minus 6 minus 24 iota, take the conjugate. Now what's a conjugate? I is replaced by minus I. So minus 6 plus 24 iota. What about the left hand side? RHS is an x plus iy form. So left hand side should be also expressed in which form? X plus iy form. So we'll just open the bracket here. This is a conjugate, remember. Conjugate means I is replaced by minus I. So this become plus 24. This is as it is. Here we just express in which form? X plus iy form. So I'll open the bracket. This into this, which is 3x. This into this, which is 5x iota. This into this, which is minus 3y iota. Here you have minus 5y iota squared. But what is iota squared? That is minus 1. So this become plus 1. I repeat, this into this 3x, 5x iota. This is 3y iota with minus sign. This is 5y minus iota squared. So it become plus. So you are getting 3x plus 5y plus, take iota common from this. So 5x minus 3y into iota equals to minus 6 plus 24 iota. Now comparing real and imaginary parts. Comparing real and imaginary part. We compare the real and imaginary parts. What's the real part here? Minus 6. Here you have this 3x plus 5y equals to minus 6. What about this? 5x minus 3y equals to 24. Here imaginary part is 24. Here this. Now solve these two equations by elimination method. Solving equations. So you'll get here x and y. Important one was this part, just express in a plus ib form. Next question. Question number 15 here. Let me take that as the complex number z. Z equals to 1 plus iota upon 1 minus iota plus, sorry, you have minus here, minus 1 minus iota upon 1 plus iota. You are asked to find modulus. Modulus can be obtained only when the complex number in x plus iota y form. So again simplification and get this form. So z equals to, do the cross multiplication, 1 plus iota square minus 1 minus iota square upon 1 minus iota into 1 plus iota. This is z into z bar. So your denominator is just x square plus y square, that is 2. 1 square plus 1 square. X square plus y square. You just open the bracket, you will get 2. Or this is z into z bar, which is x square plus y square. What about this? If you expand this here, first term is 1, last term is also iota square, which is minus 1. So you are left with just middle term, 2 iota. Minus, your first term is 1, last term is iota square, which is minus 1. So you are just left with here minus 2 iota. Middle term, which is minus 2i. So finally we are getting 4 iota by 2. So z equals to just 2 iota, and therefore modulus z equals to root of real part square, which is 0, plus imaginary part square, which is 4. So you will get 2. So magnitude of the complex number is here 2. Question number 16 here. You are given x plus iota y whole cube equals to u plus iv. Now here what we do is we just express this one in x plus iota y form. This is already in x plus iota y form. So I'll expand this. So you have here x cube plus iota y cube plus 3x square into iota y plus 3x into iota y the whole square, and RHS as it is, that is u plus iv. What we did, just expanding LHS, nothing more than that you did. Okay. Now let me simplify the x cube as it is here. Iota cube is iota square into iota. Iota square is minus 1. So this is minus y cube into iota. This is 3x square y into iota. Here somewhere you have iota square, which is minus 1. So 3xy square. Iota square is minus 1, which I have written here. Okay. So you have x cube minus 3xy square. Take iota common from this. So y cube with minus sign plus 3x square y into iota equals to u plus iota v. This is real part, this is imaginary part. So just as we did earlier, comparing real and imaginary part. Comparing real and imaginary parts. So we'll get u and v. So what is u? Here real part. Here x cube minus 3xy square. What is v? Minus y cube plus 3x square y. So you got u, you have v. Now what is LHS? Just place there. Now left hand side is u by x plus v by y. So by x, which is x squared minus 3y squared, plus, now dividing by y here. So this is here minus y squared plus 3x squared, dividing by y here. Okay, so you have x squared minus 3y squared minus y squared plus 3x squared. So we'll get the 4x squared minus 4y squared. That's what your RHS. Take 4 common, x squared minus y squared, which is right hand side. The next question is question number 17 here. This is an important example. Your two complex number with magnitude of beta equals to 1, alpha and beta be two complex number. The question is here, get the value of this expression. Beta minus alpha upon 1 minus alpha conjugate into beta. Now this is equals to, this is theoretical sum. We'll do like this. Instead of 1, I'll put the magnitude of beta. Minus, this is as it is. Now this is equals to, if you remember in the properties of modulus, we already written that modulus you can write complex number into its conjugate. You just recall this, modulus of z, the whole square, it is z into its conjugate. Now here you can write whole square because 1 square is 1. So we have this. If you want, you can write here whole square. It will do even if you are not going to write. Whole square you can write because 1 square is 1. And what's the modulus of z the whole square? That is z into its conjugate. I've used this property here. What is common in the denominator? Beta. So I'll keep 1 upon modulus beta outside. What we get here? Beta minus alpha upon modulus of beta conjugate minus alpha conjugate. Now this is 1, so outside we have just 1. Now here beta minus alpha as it is. If you recall, you can write the whole conjugate here. You know this property, z1 plus z2 the whole conjugate equals to z1 conjugate plus z2 conjugate. So instead of this, I wrote this here. Now again the property of modulus, modulus of the numerator upon modulus of the denominator. This is the property of modulus we have used twice earlier. Modulus of z1 upon z2 equals to modulus of z1 upon modulus of z2. This is also one of the property of the modulus. If you remember, we already stated magnitude of any complex number and its conjugate are always equal. So this is like z and this is like z conjugate. So both are always equal. So answer is 1 here. This will get cancelled. Question number 18 here. Find integral solutions. Find number of, the question is number of non-zero integral. Integral means integer solution. Integral solutions of these equations. Solutions of this equation. equation is here 1 minus iota inside the modulus the whole raised to x equals to 2 raised to x. This is the equation. What is 1 minus iota? You know, with modulus it is root this square plus this square, which is root 2. The whole raised to x equals to 2 raised to x. Root 2 means raised to 1 by 2. So this is raised to x by 2 equals to 2 raised to x. Both bases are same, so you can compare the exponents. So x by 2 equals to x. That is x equals to 2x. You take 1 on the other side, so x equals to 0. So it has only one solution, and which is 0. You are asked for what? Non-zero integral solutions. So therefore number of non-zero integral means integral solutions equals to 0. It has no solution which is other than 0, and it is integral. Remember, it has only one solution, and which is 0 only. You are asked for non-zero integer solutions. So number of non-zero integral solutions equals to 0. Okay, now next question number here 19. If you just look at what you want to prove, you will realize immediately. So in the question number 19, you are given this a plus iota b, one complex number, c plus iota d, another complex number, e plus iota f, third complex number, g plus iota h, fourth complex number, equals to a plus iota b. Right hand side is also one complex number. Now you just look at that required expression, you will immediately realize that required expression is magnitude of this, magnitude of this, magnitude of this, magnitude of this. So what we do, we just take modulus on both the sides, taking modulus on both the sides, magnitude means modulus. So what we'll get here? Modulus of a plus ib, c plus id, e plus if into g plus ih equals to modulus of a plus ib. Now this is the property of modulus. You can write individual modulus here. Modulus of a plus ib, modulus of c plus id, modulus of e plus if into modulus of g plus ih. For multiplication and division, you can take individual modulus, remember. So which property I have used here? This one. Modulus of z1 into z2, that's equals to modulus of z1 into modulus of z2. This property I have used. For product, you can do individual modulus. For division also, you know, we already used, you can do individual division. If you have this, you can write this upon this, remember. Okay, now you know this is root of a square plus b square. So you are almost through here. So what is the first one? Root of a square plus b square. What is this? Root of c square plus d square. What is this? Root of e square plus f square. Similarly here, root of g square plus h square equals to root of a square plus b square. And now for required expression, just squaring on both the sides. So a square plus b square into c square plus d square, here e square plus f square, g square plus h square equals to a square plus b square. Proved. That's what you want. Let's come to last question here, 20th number. 20th question, you are given this here. 1 plus iota upon 1 minus iota, the whole raised to m equals to 1. What's the question? Find the smallest value of m, least positive value of m, remember. So the first thing in complex number is what? You express in a plus ib form inside this. So we keep that power m as it is, and we'll just simplify. How do we simplify? Multiply and dividing with the conjugate. So we have this. We keep that whole raised to m as it is here, 1 as it is. We want to find m for which this become 1. That's a question. Remember, this is given to us. What we want to do? We want to find the m for which this become 1, and not any m, that's the smallest positive integer. Integral means integer, you know. So we simplify this first. What is denominator? Z into its conjugate, which is x square plus y square, which is 2. X square plus y square, which is 2. What about this? 1 plus iota whole square. What is that? 1 plus 2 iota, and the last one is minus 1. Okay, so you are just left with 1 will go all the way, 2 will go to cancel. You are getting just iota raised to m equals to 1. Now you know, find the smallest value of m for which iota raised to that m becomes 1. So you know the smallest value is iota raised to 4 equals to 1. So what is m? M has to be 4. Remember, if I write iota raised to 8, which is also 1. If I write iota raised to 12, which is also 1. But this is the smallest. What's the question here? List smallest positive integer. That's the question. Integral means integer. So therefore, iota raised to m equals to 1 is possible only when m is 4, remember.